Hi, this video is about latitude, longitude, and finding distances between cities that are quite a far ways apart from each other. So we need an Earth on here. One way to get the Earth it would be to put a sphere of radius 3,959 miles on there, but that would not be good. So we're just going to scale it down like a little globe. So I'm going to just make R to be 3.959. That's the radius of the Earth. I guess I'll make that a big R rather than a little r because it's pretty big. So the sphere we want is x squared. We want it centered at the origin. So x squared plus y squared plus z squared equals r squared. Big R squared. Okay. So should go near 4, right? Let's make it look a little bit more like an Earth. Let's make it easier to see through. Make it blue. Okay. So it's like a water world. So you can see that the z-axis could be like our axis of rotation, and then so the equator is defined by the intersection of the xy plane with it. So how could we get that? How could we get the equator? Well, let's see. So you would be looking straight down at the xy plane like that. Okay, and so we want this circle. So let's see what we can do here. So we're coming out to about 4. How can we parameterize this curve? So what we could do is we could have a couple of unit vectors at right angles to each other. So what's this little guy? That is 1, 0, 0. And this is 0, 1, 0. Okay, they're both in the xy plane. We need to scale these by r and then use a linear combination of these two to get points on here. That makes sense, right? So we need to scale this thing here by r. Okay. And then we need to multiply it by something. And then we're going to take a multiple of the other one. And we want it to land on here. So ideally when t is 0, we would be here maybe. So we would want this to be 1 and this to be 0. But then at some point we would want to have this one be 0 and this be 1. Then negative 1, 0. So that's suggesting a trig parameterization. So we'll just do cosine t because that is 1 here. And this is 0 here. But then it becomes 0, 1, then negative 1, 0. Does what we want. So if we multiply all that out, we get this vector function. R cosine t, r sine t, 0. That, and if t goes from 0 to 2 pi, we'll see our equator. So I'm just going to put a curve in here. Oops. Okay, curve. This needs to be r cosine t. Okay. This will be r sine t. and this will be 0. And then t is going to go from 0 to 2 pi. We can just type in pi. What? Oh, used the wrong r. Yeah, I know. I probably should have stuck with the lowercase r, but I didn't. Okay, so we get the equator. Okay, there it is in all of its glory. So we don't need this plane anymore. We have the equator. Now how do we get the other lines of latitude? So what does latitude, so I've got longitude up here, but here we can see latitude. What you do is you just kind of go off by angles out of the center of the earth. So you have one going to the equator, then you go up by a certain amount, so 15, 30, 45, 60, 75, 90. Let's do that. Okay, let's do that. So okay, so we need to look at a cross section where we actually see the z-axis, and it doesn't matter which one I use, I'll just use the x-axis here. So now we have the North Pole here and the South Pole here, and this is the equator, and this is the center of the Earth. So we'll go off at, say, a 15-degree angle. Okay, and we're going to make a new circle right there. So what we're really going to do is intersect the sphere with a plane of a certain height. So we need this height, and it's this height here. So by alternate interior angles, that's 15 there. I'm going to make this bigger. Okay. Let's make this bigger. So here's the North Pole, South Pole. We're going off at a 15-degree angle there. We're making a new circle by intersecting the sphere with that plane. So that'll be z equals something. So we get 15 here by alternate interior angles because I'm making this circle parallel to this circle. So what is this length? So the sine of it is this z over here, which is our big R of the Earth. So this has to be r sine 15 degrees. And the radius of the circle, I'm going to make that, I guess, little r, is big R cosine 15. Okay, but first of all, I'm going to intersect it with the plane z equals big R sine 15 degrees. Okay, so the plane that I want is z equals big R times the sine, but it has to be in radians, so I'm doing 15 and then pi over 180 is the way you convert to radians. Okay. So we need to now parameterize that circle of intersection. But it's the same thing, it's just the z coordinates a little higher now. See how the radius is just different, and the radius we said was r cosine 15 degrees. So to get this circle here, we'll take this kind of thing, we can take all of that and put it down here, but the radius isn't r anymore, it's r cosine 15. Okay. And we're not at z equals 0 anymore. The height of it is r sine 15. 15 pi over 80. That should do it. Okay, so it did make the correct circle for us. So we still have the equator, but now we have this new one. Alright, so how do we get the rest? Well, we just changed the 15 to 30 or something. So let's take this thing, copy it, put it down here, but change the 15s to 30s. And then we should get a smaller, higher circle. Okay? It's looking good. Do it again. Make them 45 instead of 30. And we need another one that's 60. So just every 15 degrees until, oops. Okay. We still need one more tiny one up here for 75 degrees. And there's no point in doing 90 because then you're just getting the North Pole. Let's go ahead and put the North Pole as a point. So that's 0, 0, R. And then the South Pole is 0, 0, negative R. Okay, so that's the North Pole. And the other one is the South Pole. Okay, so we have the top half. Now let's get the bottom half. We just do these with negatives. So copy, oops, select all, copy, put it down here and just put negatives everywhere. Okay. Right, we skipped the 15 one. So I'll just take this because it's already got the negatives built in. Let's put this as 15, 15, 15. And we need it for 60, or 45 actually. I don't skip anything. $60. And then 75. So this is kind of fun. There, we got our poles and we have all the lines of latitude I care to put on there. You could put all 180 if you really, really wanted to. But we're not going to do that. Okay, pretty cool looking. Now what about longitude? Well, the thing about longitude, so latitude has this sort of natural equator because it's the great circle that is perpendicular to the axis of rotation. Okay. Now note that these other ones are not great circles. They're smaller circles. Great circle has to have the diameter the same as the sphere. Okay. What about meridians, though? What about lines of longitude? Those go through both poles. Okay, so they have that natural definition, but how do you decide what else they go through? There is no natural choice for that, really. It's kind of arbitrary. The way they do it on the Earth is they go through Greenwich, England. Like they have this prime meridian. They call it the prime meridian, and it goes through England. Goes through this city called Greenwich, England. It's totally arbitrary, but that's what they do. I'm going to arbitrarily say that Greenwich, England is above the x-axis, right? It's on one of these parallels above the x-axis, right? You got to choose some arbitrary point on the sphere that it goes through besides the North and South Pole. You need 3 points in the center. So let's just have it go through the x-axis. So then we would be we would want it to eliminate the y-axis there. So we're going to hold y as 0 to make it kind of go have a plane with that contains the z-axis and the x-axis. So we'll do y equals 0 to get that meridian. Now that gives us 2 meridians. The prime meridian is the one on this side. That's 0 degrees. Then the other one will be 180 or negative 180, whichever you prefer to call it. But we have to parameterize that circle now. Alright, and it's very much like we did with the xy plane, except it's the xz plane, so you would just make this a z. So instead of 0, 1, 0, it's 0, 0, 1. So the parameterization that we would get, you would just kind of move this to here, right? So we want to use r cosine t 0, r sine t this time. And that ought to do it for that meridian, that pair of meridians. Okay. So let's say that we're doing the curve. This is r cosine t 0, and then r sine t, and t goes from 0 to 2 pi. Okay. There it did. So we got it. It goes through that plane, which we no longer need. Okay. So all of these circles, they're all going to be great circles this time, and they're going to always, because they're always going to go through the North and South Pole. So now we want to go 15 degrees. We just kind of want to rotate that whole thing by 15 degrees. So I kind of want a line now going like this on the XY plane. So let's figure out what's, so that, well, first of all, we need that plane, right? Now, we need to think about that. So we're looking at the XY plane. We're cutting it with a line, but really we're cutting it with a plane. So what we just did is we cut it with that plane, y equals 0. But now we want to go off at a 15-degree angle. Okay. Now, how is a plane defined? A plane, you need a point on the plane. Now, all these are going to go through the origin. They're all going to go through 0, 0, 0, the center of the Earth, which is very convenient. But so we also need a normal vector. Now, for this plane, the one that went through the x-axis, we could have used 1 or 0, 1, 0 as the normal vector, right? But now it would be nice if we could get, so it has to be perpendicular to the plane that we're interested in, so it has to make a right angle there. But is there a, so by rotating the whole plane by 15 degrees, I'm also rotating this by 15 degrees. So I get a 15 here, and I get a 15 here. So what are the coordinates, or what are the components of this vector? Well, the height, so this length right here is the cosine of 15. degrees, right? Because this is a 1. We're using a unit vector there. So this here is the negative sine of 15, because it's backwards on the x-axis. So and this vector is in the xy plane, so it's got a z component of 0. So we're at cosine 15. Oh, gotta be careful there. The x component is negative sine 15. The y component is cosine 15, and the other one is 0. So that's going to be our normal vector. Okay. So we're dotting that. We're dotting negative sine 15 degrees, cosine 15 degrees, 0 degrees. That's our normal vector. We're dotting it with x minus the xyz minus the origin. That's the equation of the plane. So we get negative sine 15 x plus cosine 15 y equals 0. That's our plane we want. So negative sine 15, now we have to do pi over 180 times x plus cosine 15 pi over 180 y equals 0. Okay, it created a plane, and that is exactly the plane we want. Okay. Now, it creates this circle, right? How do we parameterize that? Now, it's much the same way as we parameterized the others. But, so, what we were doing for all these circles is we get a couple of unit vectors and scale them by r, and then do the cosine sine thing to make them go in a circle like that. So now what are the vectors that we're using? Well, we need a pair of vectors in the plane that are unit. Okay, so let's just look at this plane for a second. Let me try to get rid of these things for now so we don't clutter everything. Okay, so see how we're intersecting the sphere like that? We just need, notice that the z-axis goes through it, right? All the axis of rotation of the Earth goes through all of the planes that define these meridians, no matter what you do. So 0, 0, 1 is in the plane. Okay, so we need that one. That's a unit vector that we'll use. Another one is got to be in, it can be in the xy plane, right? And to make it a unit vector in this direction, let's just do the math on it. So, you know, we went off at a 15-degree angle from the x-axis. So we want this to be 1. So this here is cosine 15, and this is sine 15. Okay. So that unit vector here has to be cosine 15, sine 15, 0. Those are going to be at right angles to each other because this is going, it's perpendicular to the xy plane, and this is in the xy plane. Okay. So we'll just use these two up in this formula. instead of these two. It's like our new basis. So cosine r cosine the times 1, and then r sine in the other. So I'll do r cosine t times this plus r sine t times this. Okay, so what is that? So we end up with, and these are big R's, right? Sorry, keep doing that. R cosine t cosine 15, so that's the constant is this, and then the variable here, plus 0. Then r cosine, or then r sine t, r sine 15 degrees times the cosine of t, plus 0. And then now we have 0 plus r sine t. So that's the parameterization of that circle. Okay, so we just have a cosine 15 cosine t, a sine 15 cosine t, and then a sine t. So let's see if we can get this circle to be parameterized. So curve we said it was r cosine 15 degrees and then cosine t. This is r sine 15 cosine t. And then the last one is just r sine t, with t going from 0 to 2 pi. Okay, awesome. And again, we just changed that angle to change the plane and to therefore change the circle. So we can bring back these things, because now we know what to do. Okay, so we've got we've got 4 meridians now. Let's just get the rest, and then to complete our mapping of the Earth. So to do that, we're just going to change the angle in here. Right? We'll just make it a 30 instead of a 15. And then we'll just keep doing that until we get around the whole Earth. So 45. And then 60. And then 75. And then technically 90, right? But then what's going to happen? It's just going to be x equals 0. So let's, rather than do all that, let's just do x equals, well, nah, let's not. Let's just make it 90, because I don't want to deal with the parameterization and all that. Okay, it'll still work doing it that way. So you can either use the negatives to get the others, or just keep going with the 15. I guess I'll do the negatives. Why not? Negative 45. Negative 60. Almost there. And then we don't need to do the last one because it would just be repeating it. So there. Now we have the whole grid of the Earth. Okay. That is how longitude and latitude work. So that is a beautiful little Earth.